Dear students, in this is the new chapter superconductivity. This is first lecture and we are going to study the superconductivity, electrical conductivity and Meissner effects. Superconductivity introduction and historical developments. The state of matter in which electrical resistivity of the matter becomes zero abruptly below a certain temperature is called superconductivity. The field of superconductivity has emerged as one of the most exciting fields of solid state physics and solid state chemistry during the last decade. The phenomenon was first discovered in 1911 by Cambridge on Camerling on in Leiden while observing the electric resistance of mercury at very low temperatures, close to 4.2 Kelvin, the melting point of the helium. It was observed that the electric resistance of mercury decreased continuously from its melting point 233 Kelvin to 4.2 Kelvin, and then within some hundredths of a degree dropped suddenly to about a millionth of its original value at the melting point, as shown in the fig 1, which is on the next slide. Similar results were obtained by using various other metals such as Pp, Sn, and In. Temperature dependency of the resistance of a normal metal and a superconducting conductor like silver. This graph between the resistance and the temperature, with the increase of the temperature the resistance of the normal matter is going to increase, and with the decrease of the temperature the resistance of the material is going to decrease. While for the case of superconductor Hg, we have seen that with the decrease of the temperature the resistance is going to decrease, but at 4.2 Kelvin the resistance abruptly becomes zero. The phenomenon of disappearance of electrical resistance of materials below a certain temperature was called superconductivity by Ohms, and the material is in this state was called a superconductor. The discovery of superconductivity aroused considerable interest in this field, since the materials with no electrical resistance and hence negligible heat losses could be exploited to fabricate powerful and economical devices which consume very little amount of electrical energy. For example, an electromagnetic made up of superconducting materials can function for years together even after removal of the supply voltage. However, due to requirement of very low temperature, it was not feasible to manufacture such devices. It is both difficult and expensive to attain the liquid helium temperature and maintain it for a long time. Thus, soon after the discovery of superconductivity, a lot of research work was undertaken to develop a superconducting material having a high critical temperature as possible. A number of materials, including various metals, alloys, intermetallic and interstitial compounds, and ceramics, were employed for this purpose. Beside all these efforts, the maximum critical temperature Tc of only 23 Kelvin was achieved in Nb3Ge, an intermetallic compound of niobium and the germanium, in the year 1977. Thus, the scientist had almost given up the hope of producing superconducting devices, for which it was necessary to have a superconductor with the transition temperature equal to or higher than 77 Kelvin. The liquid nitrogen temperature, if one not the room temperature, in 1986, Bednors and Muller reported their discovery on the lithium barium copper oxide system of ceramic superconductors, which showed Tc equal to 34 Kelvin. Thus, contrary to the previous findings, a new class of ceramic superconductors was discovered which showed critical temperature considerably greater than that of the metallic superconductors. They named these materials as high Tc ceramic superconductors. They were awarded the Nobel Prize in 1988 for such an important discovery, which created an unprecedented worldwide interest in the field of oxide ceramic superconductors. In 1987, a ceramic superconductor of the composition, yttrium barium copper oxide was discovered, which showed Tc equal to 90 K. In 1988, the value of Tc further shot up to about 125 Kelvin for the thallium cuprates. Table 1 gives some data on the superconductors in chronological order. It would be apparent from the following discussions that the superconducting state is a distinct phase of matter having characteristic electrical, magnetic, thermodynamic and other physical properties. The most easily observed characteristics of the Bell superconductors are the zero electrical resistance and the perfect diamagnetism. This is the table which is providing the critical temperature of the superconductors of the different materials, different compounds, and the class of the materials and the crystal structures and the type of the materials. Electrical resistivity. As described earlier, a superconductor exhibits no electrical resistance. The resistance of a superconductor suddenly drops to an extremely small value near the transition temperature as shown in the fig 1. The careful investigations have shown that the resistivity of metal in the superconductor state drops to less than 1 part in the 10th power 17 of its value in the normal state. Perfect diamagnetism are the Meissner effect. Meissner and Ostenfeld discovered in 1933 that a superconductor expelled the magnetic flux as the former was cooled below Tc in an external magnetic field. That is, it behaved as a perfect diamagnetic. This phenomenon is known as the Meissner effect. Such a flux exclusion is also observed if the superconductor is first cooled below Tc and then placed in the magnetic field. It further follows that the diamagnetic behavior of a superconductor is independent of its history as illustrated in figure 2. On the next slide, it also follows from this figure that the Meissner effect is a reversible phenomenon. Since B is equal to 0 inside the superconductor, we can write B is equal to mu naught into H plus M is equal to 0. H is equal to minus M. Therefore, the susceptibility is given by chi is equal to M by H is equal to minus 1, which is true for a perfect diamagnetic. This is the diagram from left to right when T greater than Tc, rho is equal to 0. Resistivity is 0 when we cooled. T less than Tc, rho is equal to 0. When we applied magnetic field on the superconductor with it, rho is equal to 0, then it's pushed out and then field removed, that is remains superconductor. And lower one, when T greater than Tc, then the magnetic field is applied, then it passes through the material, and when cool, then it's pushed out at T less than Tc, and when we again remove the field, that is superconductor. A superconductor showing a perfect diamagnetism is independent of its history. It is interesting to note that the perfect diamagnetic behavior of a superconductor cannot be explained simply by considering its zero resistance. Such a perfect conductor would behave differently under different conditions as illustrated in the fig 3 on the next slide. Since the resistivity rho is 0 for a perfect conductor, the application of Ohm's law E is equal to rho J indicates that no electric field can exist inside the perfect conductor. Using one of the Maxwell's equation, that is del cross E is equal to minus partial B partial T, we obtain B is equal to 0. Conductor, rho is equal to 0. Cooling, perfect diamagnetic, rho is equal to 0. Magnetic field applied, that's pushed out, field removed, we get. And if the material is rho does not equal to 0 and applied the magnetic field, it passed through the material and we cooled, rho is equal to 0, field removed, that is there is no electric field inside the material. Thus, the magnetic flux density passing through a perfect conductor becomes constant. This means that when a perfect magnetic conductor is cooled in the magnetic field until its resistance becomes 0, the magnetic field in the material gets frozen in and cannot change subsequently irrespective of the applied field. Thus, this is in contradiction to the Meissner effect. Thus, we conclude that the behavior from that of the perfect conductor in the superconducting state may be considered as a characteristic thermodynamic phase of the substance in which the substance cannot sustain steady electric and magnetic fields. Hence, the two mutually independent properties defining the superconducting scale state are the zero resistivity and the perfect time magnetism. That is E is equal to zero, B is equal to zero. तो जब मैग्नेटिक फील्ड चेंज नहीं हो रहा होगा किसी भी सुपर कंडक्टर के अंदर, तो उसके अंदर क्या है, इलेक्ट्रिक फील्ड भी एग्जिस्ट नहीं करेगा. E is equal to zero, B is equal to zero. If a superconductor is cooled in a magnetic field B below the transition temperature Tc, then at the transition the lines of the induction B are pushed out. This is called Meissner effect.